Hello and welcome to Lab 5, Magnetic Braking with Faraday. In this lab we're going to be dropping a magnet inside of an aluminum foil tube and tracking how long it takes for that magnet to fall and come out the other end of the tube. And our purpose is going to be to observe and learn how the falling magnet results in an induced current and resulting magnetic force on the magnet that opposes gravity. The preview for our final results includes our experimental fall time of 0.58 seconds and the computer model fall time of 0.551 seconds. So a little bit of difference there. Some of the physics principles we're going to be using include the formula for a magnetic field from a dipole at a position given the magnetic dipole moment. And then we have the equation for EMF given the derivative of flux and the number of rings. And then we have the equation for the derivative flux through a ring given the radius of the ring and the distance of the ring from a dipole. We're going to be using all of these in our model, as well as Ohm's law, that current is equal to EMF over resistance. Here is our experimental data, our measurements for the tube as well as the magnet, and then all the times that it took for the magnet to fall through the tube. Here we have our Glow script code. We start with our constants for the tube, our creation of the tube right here, and then we have the constants for the magnet as well as our initializations, and then we get to the function for the dipole moment that we created in lab 3, and then our function for calculating the derivative of flux over time. And the way we're going to calculate this is by taking a ring or a small piece of the tube and the magnet and finding the d-flux dt of that and then iterating through to find the total. And so we're going to start with a radius for one of the rings, finding the distance between that ring and the magnet. We're going to take the speed of the magnet as it's falling down, so the speed at a given time, and then we're going to plug it into that formula that we showed earlier, and that will give us the d-flux dt. And then we have our iteration as discussed before for calculating the magnitude of the force on the magnet. And so we have our d-flux dt calculation here, our current as a result, again using Ohm's law where we have the EMF over the resistance. And then down here we calculate the magnitude of the force on the magnets is going to be equal to the current through the ring times 2 pi times the radius of the ring times the sine of the angle made by the magnetic moment vector and the magnetic field vector at the point on the ring, and then multiplied by the magnitude of the magnetic field at the ring. And that is going to give us the magnitude of the force on the magnet at a given ring, and so we will add all of those up and end up with the overall magnetic force on the magnet. Once we run this, it takes about half a second, a little over half a second, for the magnet to go through the tube, and this is what our velocity over time graph looks like. We can observe that as the speed increases, the acceleration is going to decrease and the velocity is going to plateau. That's because as the speed gets greater and greater, the magnetic force is also going to increase and begin to counteract gravity. Now, if we're curious what would happen if the resistivity were to approach 0, we simply have to look at the relationship between the current and the resistance, which is inversely proportional. We'll see that as the resistance falls to 0, the current will shoot up to infinity, which will cause the force to increase significantly higher than the force of gravity, which will cause the magnet to shoot way up. Now let's ask, how do the results from our experiment differ from the model, and what is the reason for this? The model was actually fairly close to the real results, though it was off by about 0.03 seconds or so. One of the causes for this could potentially be that the orientation of the magnet changed somewhat in midair in real life, so it's not going to be able to fall straight down on axis the whole way. And so now we move on to these questions. We answered this one a little bit earlier, so we'll move on to what if holes or slots were cut into the tube? How would this affect the ring currents in your model? And the answer is that many of the ring currents would be interrupted, and this would result in a lesser induced magnetic force acting on the magnet, so it would fall faster through the tube. So in conclusion, we're able to model the motion of a magnet pretty accurately as it falls through a tube of aluminum foil by using Faraday's law, Ohm's law, and Lenz's law. And the phenomenon of magnetic braking does make sense with an understanding of induced currents, magnetic fields, and the relationship between motion and the forces on an object. Thank you for listening to this lab.